Can you see my screen?
Yes, sir.
Okay, thanks. Okay, so in the last class, we saw I give a very high level overview of what information theory is all about and where it is used. And at a very heuristic level, I mentioned what information is as a reduction in uncertainty. And I'll elaborate on that a bit in this particular lecture. And then I'll show the connections between information and compression. Yes, any questions? Hello? Yeah. So please mute yourselves and unmute yourself only if you want to ask a question. Thanks. Yeah. So yeah, I won't be monitoring the chat window over here. So if you have any questions, then just directly unmute yourself and ask. You don't need to raise your hand or anything. When you're asking a question or answering something, please also mention your name so that I get to know all of you. Right. So I mentioned that information is in some sense a reduction in uncertainty. So let's explore that in a little more detail. Now the example that I gave in the previous class about this reduction in uncertainty is for example text prediction. So when you go to Google and then type something, then Google keeps trying to predict what you're going to type, right? And in some sense, the more you type, the more information you're giving it, and it can predict with a greater accuracy, right? So initially, when you go on Google, yeah. So when you go on Google and you click something, you don't know what you're going to type, but then once I start typing, there's a list of possible choices that you have. So there is a lot of uncertainty at this point as to what I'm going to type. But then maybe once I type headphones, now you're giving it more information. So in some sense, you're reducing the uncertainty about what you're going to type, and you're providing information to Google as to what you want to know. Okay, so let's try to formalize this a little bit. Okay, now let's consider the problem of tossing a coin. Right. So the problem is that of tossing a coin, and let's consider two particular coins. One is a perfectly fair coin, so the probability of getting a head is half. Right. So before tossing the coin, I don't know what the outcome is going to be. Right. So it's equally likely that I'm going to get a head or a tail. So if I want to guess whether the outcome is head, then right now there's some amount of uncertainty, and once I know the outcome, I get some amount of information about what the outcome is. Now in contrast, let us take the example where I have a biased coin. It's a horrible coin, but the probability of a head is, let's say, 0.0001, or let me put it slightly differently. So at one extreme, let us assume that so one is a fair coin. The probability of head is a half. On the other hand, I have a Cholet coin. If you watch the movie Cholet, then you know that a Cholet coin is one where both the sides of the coin is a head. So the probability of getting a head is always equal to 1. Right? So if I toss this Cholet coin, even before tossing the coin, I know that it's going to be a head, right? And so in some sense, I'm getting no information after I observe the outcome of the tossing of the coin. Right. So initially there is no uncertainty about what the outcome of the toss is in this particular case. Right. So let's look at something in between. Right. Let's suppose that the probability of getting a head is say 0.0001. Okay. So now do you think that do you think the outcome of this coin gives you more information than the outcome of this coin, or the other way around? So does a fair coin, is the outcome of a fair coin giving you more information than the outcome of a biased coin with probability 0.0001, or is it the other way around? Do you think that the outcome of a biased coin gives you more information than the outcome of a fair coin? Yes.
Maybe outcome of the fair coin.
So outcome of the fair coin, yes. Does it give more information or less information?
More information.
Right. So in some sense, the outcome of a fair coin is in some sense more random, whatever that means. So it's more random, and therefore, when you observe the outcome, you are getting more information. If, of course, assuming that by information I mean a reduction in the uncertainty. Right. Okay. So this, I guess, at a very high level is close to the problem of text compression. So let's suppose that we want to predict English text. So right now we've seen that if we toss a coin, so the more sort of random the coin is, that is, the more fair the coin is, the more uncertainty there is as to what the outcome is going to be. And therefore, by observing the outcome, you're getting more information. So in some sense, a fair coin is more informative than a biased coin. Right? And let's take that in the, let's look at the
So,
problem of, yes, please.
so in the
Yeah, so
case
also,
of,
can you also please mention your names
uh,
before?
yeah, I'm Chaitanya.
Yeah, go ahead.
Uh, in the above, like in the previous case where we googled some stuff, like
Yes,
that when you're entering text, the randomness is decreasing because the word is easy to predict.
exactly.
The probabilities are already fixed. Like the probability of head is some 0.001,
True,
and we tossed the coin and we got some result.
true.
And I didn't understand in what sense did this reduce the uncertainty. Like we are already sure that the uncertainty remains the same even for the next case.
Okay. So when I mean reduction in uncertainty, so you know that you're going to toss a coin, right?
Yes.
So you know that you're going to toss a coin, but before tossing the coin, you don't know what the outcome is, right?
Yes.
Correct. Now, in the case of a fair coin, you don't know what the outcome is. It's 50-50. It could be a head or it could be a tail. Right? After observing the outcome of the toss, after tossing the coin, you see that maybe it's a head, right? So
Yes.
the outcome of the coin has given you some information, right? So initially you didn't know what it was. Now, after observing the outcome, you know something about the outcome of the coin,
Yes, sir. So we
right?
are
So
seeing.
this is what I mean by information, right? So you
Okay.
got some information, but right now we haven't quantified the amount of information we've got, right?
Got it, sir. Thank you.
On the other hand, if I have a biased coin, say probability of head is 0.0001, again, there is some uncertainty, but you know that it's very likely that it's going to be a tail, right? So once you toss the coin, maybe you observe a tail. Yes, you've got some information, but at least at a qualitative level, this information that you've got is less than what you would get after observing the outcome of a fair coin. So that's the only point that I wanted to make. Right? So in some sense, if I have a source which is producing, say, text or it's also or anything else, the more random it is in some sense, the more informative it is, and we'll sort of formalize this in this particular class. Okay, so let's look at English text, right? Okay, so we have English text, and we had the original problem of predicting what we're going to type. So initially you don't know what you're going to type, but then once you type, as you keep typing successive letters, you're getting more and more information, and by the end of the sentence, you know exactly what it is. So after observing the sentence, you got some information, and that depends on what the uncertainty was. Okay, so how is this? So I claim that this is very closely related to the problem of text compression, and and again, we leave this as a little bit of a mystery now, but at a high level, if we look at the problem of compression, okay, so what is the problem of compression? The problem of compression is the following: you are given a file. Let's say that it is a text file. Right? Now I want some kind of an algorithm which does the following. If you feed in the text file as input, then it outputs another file, which we'll call the compressed file. Right? So it outputs a file, which we call the compressed file, and hopefully the size of the compressed file is smaller than that of the original text file. But that is not enough. We also want to be able to recover the original text file using another algorithm, which we call a decompression algorithm. Right? And this is what we do. For example, if I go to so if I take a particular text file and I try to compress it, so there are a number of compression algorithms, but I compress it, I get a file. So the size of the original text file is 428 kilobytes. It's down here. And the size of the compressed file is much smaller than 428 kilobytes. It's roughly 158 kilobytes over here. So that's the problem of compression. But at the same time, I can also extract this. So there's a decompression algorithm, which will give me the original file once I decompress. So in some sense, I'm not losing any information about the original text file. I'm throwing the word information around very loosely without having completely defined it, but you know what I mean, right? So if a compression algorithm is good, then of course, so the compressed file should contain all the necessary information about the original text file, but nothing more. So in some sense, you are reducing the amount of redundancy which is already present in the text file. So let us see what that means. Now let us suppose that you want to convey a message. So let's look at the following problem where uh, where suppose that you have say you have an army which is okay. So let's consider the case where you are the general of a particular army, and your goal is to attack a particular country, or maybe you want to defend yourself against an attack by another army. Okay, so you have all your troops stationed in one particular location, and you know that the enemies can attack from one of two locations, either from some hills or from the valley, right? And to know whether it's coming from the hill or the valley, you station a particular say a sentry somewhere on the hills, and the sentry is going to convey is going to sort of give you information as to whether the enemy is coming from the hills or from the valley, right? So one way of conveying this information is that he's going to say enemy coming from the hills or enemy coming from the valley. But if you wanted to represent this using a minimum number of bits, because let's say that bandwidth is very costly, so if how many bits of information is really being conveyed by this sentry?
Two,
Why is it 2 bits?
either from valley
Like
or
one.
either from
So
hill.
so there are two choices, right? There are two choices, either hills or valley. But how many bits do you
Single.
need to represent this?
One
It is
bit.
just a single
So
bit,
one bit.
right? So for example, so I'm assuming that sorry. Yeah. So you know that the troops are coming, you know that the enemy is coming, but you don't know whether it's from the hills or the valley. So what the sentry can do is send a 1 if they're coming from the hills and 0 if they're coming from the valley, right? Any questions? Okay, so one bit is sufficient to represent the information as to whether they're coming from the hills or from the valley. So this message that the general is getting contains exactly 1 bit of information, right? And and that is our goal really when we talk about compression of a file. So there is, say, English text where there is a lot of redundancy. So here in this particular example, you could say valley or hills, but valley is one word in English text, and if you and in its raw form contains much more than 1 bit. But the amount of information contained in this message is just 1 bit. It's either valley or it's hills. So there are only two possible choices, and therefore this valley versus hills contains 1 bit of information. Now, similarly, you can model English text. There are several mathematical models for it. And, and if a compression algorithm is good, then the compressed file size, in some sense, should give you the exact number of bits of information, right? And that is indeed what we'll use as our measure of compression. So we have a text file. Maybe it is of size n bytes. A compression algorithm takes this n byte file and gives and outputs a compressed file, which is maybe k bits in size. But this contains everything that you need to know about the text file. In particular, you can recover the entire text file from the compressed file, right? So it has all the information content that is required, and these compression and decompression algorithms ensure that you can recover the text file from the compressed file. So if this compression decompression algorithm is optimal in the sense that it contains no additional redundancy than what is absolutely required, then k bits is the amount of information that is contained in the text file. Okay, and so if a compressor is good, if a compressor is optimal, then the number of compressed bits, that is the file size of the compressed file, is equal to the number of bits of information contained in the file. Okay, so in some sense, the compressed file size is proportional to the information content of a particular source. So let's do some experiments to sort of justify this. So here I have a bunch of text files. All of these are English text files. These are kind of novels which are freely available. Let's see what I have here is The Adventures of Tom Sawyer by Mark Twain, and it's A Tale of Two Cities by Charles Dickens, and so on, a number of English text files. You can get a bunch of English novels freely available at this website called gutenberg.org. Now I encourage you to run this experiment on your own, but I'm going to take these English text files. Make sure that the English text file that you have is reasonably large. Don't take very small text files, something close to a megabyte or so. So this text file is 807 kilobytes. So this is 807 kilobytes. This is 1.1 megabytes and so on. Okay, so I'll compress each of these files and find the ratio of the compressed file size to the original file size. Okay, so the compressed file size so the original file size is 807 kilobytes, and the compressed file size is 288 kilobytes. So the compression ratio is 288 divided by 807. So that's roughly 0.3569 for this particular file. Now I'll take another file and compress it. The compressed file size is 379 kilobytes. It's 379, whereas the original file size is 1.1 megabyte. Oops. So it's 379. It's roughly, so it's 379 divided by, so it's 0.34. Take another file. So compressed files. So the compressed file size is 1.2 megabytes. The original file size is 3.4 megabytes. So it's 1.2 by 3.4. So that's again roughly 0.35, and so once again it's 320 divided by 883. It's 0.36. So we're hovering around the 0.35, 0.36 range. So no matter which so as long as you have an English text file, a valid English text file consisting of proper English sentences, and as long as the file size is reasonably large, at least roughly a megabyte or so, the ratio of the compressed file size to the original file size is the same. So what this says is that the amount of information content per bit of English text is roughly 0.36. So every time you observe, say, 1,000 bits of English text, you are getting roughly 300. So you're getting roughly 362 bits of information. So every 1,000 bits of English text contains roughly 360 bits of useful information, right? And that is because there is a lot of redundancy present in the English language. So this is one particular experiment. Let's run another experiment. So here I'm going to take I have some programs that I've written. So, I have a Python program here which lets me generate random zeros and ones. The probability of whether it's going to be a zero, it's a one, is this quantity, is this variable p, and by changing p, I can change the amount of randomness in the source. So I'm going to generate 10 to the 6 bits, so a million bits, and store it in a text file. Okay, and let's see what happens. So let's start with say p equal to 0.5. Okay, so it's going to take a few seconds. So the file size is 1 megabyte over here. Now let's see what happens when I compress this file. Okay, so I compress this file. The file size now is 140 kilobytes. Okay, so if I compress this perfectly, this sequence of, if I compress 1000 bits, where each bit is IID Bernoulli half, then the compressed file size in this particular case turns out to be 142 kilobytes. Okay, so now let's change some of the parameters. So let's change this 0.5 to maybe 0.005. Zero 5, and run it once again. So this is my file. It's still 1 megabyte because there are 1000 bits. Now let's compress this. Now I see, so originally it was roughly around 140 kilobytes. Now the compressed file size is only about 12 kilobytes. It's just 12 kilobytes. So if I have 1000 uniformly random bits, then I can bring it down to just 140 kilobytes. But now if it is a biased coin, if the probability of a 1 is reasonably small, then the file size now becomes just 12.9 kilobytes. So in some sense, this is more compressible. Right? So there are, most of these are zeros, there are just a few ones in between. So that reinforces our intuition that a biased coin contains much less information than a completely fair coin. So any questions until now?
Hello, sir.
Yes.
Sir, this is not a question, but I don't know if it's for everyone, but there's a little lag between audio and video.
Oh, I see. Okay, I'm not sure what I can do about that. So yeah, I agree that there is a little bit of an issue with Microsoft Teams. I have noticed a bit of a lag. But how so roughly how much is the lag? Is it less than is it a second, or is it like few seconds?
I don't know, it's just a little less.
I'm also noticing.
Sorry, how much is the lag roughly?
It's over a second, a little over a second maybe, or yeah, just a second. Yeah.
Okay,
Nothing
okay.
more about it, but yeah.
I see. Yeah.
Sir, I just have a question.
Yes, please. Yeah. So once again, I keep reminding you. Just tell me your names before you ask.
Sir, this is Anurag. So
Okay.
you said information is decreasing the uncertainty, right? So
It's a
suppose
reduction in, yeah, sure.
yeah. So if we increase the uncertainty, can we call that deletion of information?
If you increase the information, well, okay. So again, I'm saying this in a very heuristic sense, but yes. So if you could somehow increase uncertainty, whatever that means, that would correspond to removal of information. But again, can you give a physical example of something like that?
Uh, so suppose we already know that there would be an exam on Sunday,
Okay.
and the instructor comes and says the exam is not on Sunday.
Okay.
That actually increased the uncertainty from like we know the for fixed that the exam is on Sunday, but then we don't know when it is. That's more uncertain than this, right?
Uh, okay. I guess you're right in some sense. But now maybe right away I'm going to give sort of a more formal definition of what I mean by information, and maybe you'll see that such a scenario doesn't arise.
Yeah.
Okay. Okay. Yeah.
Sir,
It's a valid point. Yes. Yes.
Sir,
yes, sir. So myself, Mauni,
Hi.
Siva Mauni. So actually, my doubt is, as now we are saying that a biased coin, like a fair coin, has more information when compared to biased. I mean, can be compressed more when compared to biased, right?
Can be compressed less in some sense.
Can be compressed less.
Yeah.
Okay.
So we saw that a fair coin, it take. Go ahead.
Does this has any relation with respect to like information content? Like as in we say that when the probability is very less, then it has more information content, something like that. I mean, unlikely event, something. So
Okay.
entropy wise.
Sure. So we'll get to entropy in a bit.
Okay.
And that is really where I'm getting to the notion of information content.
Okay. I mean, I'm a bit confused between these two terms. So these two are not linked, right?
Sure. Well, they are linked. And when I'm saying information, I'm using it in a very loose sense. I have not. So this is just to get a very heuristic idea of what we mean by uncertainty. So the more uncertainty there is, if you observe the outcome, you get more information. That is the only point that I'm trying to
Yeah.
make.
Okay.
Right?
Okay, sir.
Okay. Any other questions?
sir,
Yes.
this is Soham.
Tell me.
So I just created a text file, and in it
Okay.
I wrote 2 sentences: a book,
Okay.
a pen.
Okay. Okay.
So the size of the text file was 14 bytes.
Okay.
So I compressed it
Uh-huh.
using RAR algorithm. So
Okay.
the size changed to 83 bytes.
Uh-huh.
So the size actually increased.
Yeah, the size increased, and that is why I said that if you're doing this experiment, you should make sure that the file size is at least a bit large, because uh, if the file size if the original file size is too small, then compression. So of course, then compression algorithms don't work very well.
So is it actually like if in a proper English essay sort of text file, then
Yeah.
there are many repeated words like
Exactly.
articles, and also they are mapped to their certain places, and then like total number of words, like if there are, we calculate 2 raised to n as total number of words, and then we
Correct.
get n bits of data per place. So that's why the
Exactly.
size reduces.
Exactly. So if it's a very small sentence, then compression algorithms don't work well, and in fact we'll see this later in a successive course on source coding. But in some sense, the two sentences that you wrote down on the text file, of course, contains less information than the compressed file itself. It's just that the compression algorithm doesn't work well. It doesn't mean that the compression algorithm is giving you the right number of bits of useful information.
So I think when compression algorithm compresses,
Mhm.
then it will calculate some data which will be used to decrypt the information, because they will find some probabilistic statistics and they will have to store it in the zip file. So when they decompress,
Sure.
they will use that data to decompress. So when the file size is extremely low, that extra data might overpower it, and hence the bigger file.
You're perfectly right in your reasoning. That is so. So when the original file size is too small, there's a lot of extra information like the header and other useless information, at least useless for in terms of the information content of the original file, and therefore the compressed file size is large. But if the original file size is large enough, then this header information takes relatively very less space, and therefore that doesn't come into the picture.
Yeah,
that's right.
Sir, I'm Chaitanya.
So,
I have
Yes,
regarding. I have a question regarding the previous code you have written. Like when we are changing the probability to 0.005,
correct.
Maybe the making of like the meeting of head is uncertain, but the when we are looking from the tail side, it is very more certain, no, sir, than previous case.
Correct.
So it has to have like it's more or less the same thing as having probability of head equal to 1 or probability of tail equal to 1. It is more or less same lines, no, sir. Like the
It's close.
decompression.
Yes.
So when you are compressing it, I don't think there must be a difference between when probability of head is 1 or probability of head is very close to 0. The compression should be of the same size.
True, I agree. Yes, that is right. So whether so again, let's do that experiment as you mentioned. So right here, so it's 0.005, right? So this was 0.005, and the file size was 12.9 kilobytes. Now let's make this 0.995. Okay, so it's 0.995 now, and this is what the text file looks like. So it's mostly ones and maybe a very small number of zeros in between. Let's compress this. I'm still getting 12.8 kilobytes. So that's a very good point, that if the probability of head is 0.001, sorry, 0.005, then the compressed file size is the same if the probability of 1 is 0.995. Right? So there is this sort of symmetry, right? Because you just flip the meaning of 0 or a 1 and you get essentially the same information content, right?
Sir, so does this mean the maximum uncertainty happens when p equal to half?
Exactly.
Okay.
Exactly. That's a very good
Sir,
observation. Yes.
sir, does this symmetry comes for every return? Like if the probability is 0.25 and 0.75,
Okay.
will it have the same size?
As 0.75 and 0.25?
Yes, sir.
Yes, it does. So let's do it.
Okay. That's all.
Sorry. So yeah. Anyway, so again, let me not do it myself, but you can try writing a code of this form, generate random bits and write it into a file, play around with the value of p and see what compressed file sizes you get. What you should observe, of course, make sure that you're writing at least say 10 to the 5 or 10 to the 6 bits into the file, because again, if it's too small, then as we discussed earlier, the compression algorithm doesn't work well, and these header information and stuff, they take more space. So write 10 to the 5 or 10 to the 6 bits into the file, and then play around with the values of p and see what you get. You should notice the symmetry in p. Yes. What's the question?
What will happen if we give p equal to 0 or p equal to 1?
Okay. So reasonably, what we would expect is that actually the information content is 0, right? Because you know that it's always going to be all zeros or all ones. But once again, that is not how a compression algorithm works. For a compression algorithm, you work with absolutely no information in the beginning. So there is some amount of header information, some extra information that is stored, and therefore the file size will be something small, maybe a few kilobytes, but not 0. Does that answer your question?
Okay, sir.
Okay, so let's go ahead and formalize what I described in a very heuristic manner. Okay, so the model that we will work with is the following, and this is something that we will use in the rest of this course. So yes, please.
Sir, about the last thing you said, like the information content is 0,
Yes.
but like we are using the fact that we know some privileged information, like all the
Yes.
values will be 1 or 0. So isn't that
Exactly.
information already?
Exactly. That's a very good point. Yes, that is indeed correct. So we will assume that we know something about the source, and given this information and given this knowledge of the statistics of the source, we will quantify the information content. So coming back to your point, so we'll use a probabilistic model to define our notion of information. So we'll start with a random variable x, and the random variable takes values from some set which I'll call script x. So this set is going to be called the alphabet. So if we're talking about English letters, then this is our English alphabet. If these are Hindi characters, then this is the Hindi alphabet. If x takes is say x is Bernoulli, then the alphabet is the set 0, 1. If we are looking at English sentences, then the alphabet is the set of all English sentences, and so on. Right? So this knowledge is already available to us. So we know that this random variable x, so we know the alphabet corresponding to this random variable x. And in this course, we will also assume that we know what the distribution of x is. So x comes from, so x is distributed according to some probability mass function px, if it is a discrete random variable, or it has a density function f subscript x, a probability density function, and we will assume that these distributions are given to us. Okay, so this is again it's a simplistic assumption, but we will but nevertheless, as you mentioned, this is privileged information, and we will assume that we know. And this is sometimes reasonable because, for example, if you're dealing with English text, then we already have a statistical model for English text. So we know that x, the random variable x, corresponds to maybe an English essay, and we know what we already have good probabilistic models for this. What we don't know is the realization of x. Okay, so once again, we don't know what exactly the English text is going to be, but we know that whatever we observe is going to be valid English text. Okay, and what we want to do is, so a priori we know that this is English text, and then someone gives you the realization of x, and this after observing this realization of x, you get some information. So initially all you knew was that this was English text, but then someone tells you what the English text is, so you observe a realization of this random variable x, and now you got some information. And this and our goal is to somehow characterize the information content in this, right? And the way we will characterize the information content is in the following way. So we'll say that if X is Bernoulli, so if X is Bernoulli half, so it's either 0 or 1 with equal probability, then after observing the outcome of X, after we observe a realization of X, then we can all agree that we've got one bit of information, right? So it's 0 or 1 with probability half. Someone tells you what the value of X is equal to, maybe it's equal to 1. Now, after knowing that X is equal to 1, it's reasonable to say that we got one bit of information. Okay. Now, if X is not Bernoulli half, maybe X is Bernoulli 0.1, then maybe it's not one bit of information. We've got maybe less or more, right? So we'll say that a uniform random bit contains one bit of information. And in fact, for a general random variable, for a general random variable X, we'll say that the information contained in the random variable X is the minimum of the expected number of bits needed to convey the value of X. Okay. So this is the minimum expected number of bits which we need to convey the value of X. Okay. So any questions?
Sir, can you repeat the last thing you said, like for general X? Can you explain it once again?
So, okay. So this is going to be my definition of the information content of a random variable. So we'll model a source which is producing something. Maybe it's producing maybe it is producing English text. Maybe it is producing bits. So a random variable is what I'll call a source, and we know the statistics of the random variable. And once we observe a realization, after we observe the outcome of this random variable, we get some information. And the amount of information that is contained in this random variable is what I will. So I define the information content of a random variable, or the information content of a source, as the number of bits, of information that is contained in this, which is the minimum average number of bits which are needed to convey the value of X. Okay, so think of it as, say, Morse code. Okay, so let us suppose that the alphabet is, say, 0, 1, 2. Okay, and I want to count the minimum expected number of bits which are needed to convey the value of X. Maybe so a priori, if you know nothing else about the statistics of X, if you wanted to represent 0, 1, 2 using bits, how many bits would you need to represent any one of these values?
2.
2 bits, right? So
One.
you could, why is it 1 bit?
It is to represent only one of the any one of the information. That's why it should be like
no,
one
right?
bit.
So you want to represent the outcome, right? And there are 3 outcomes, right? So basically what I'm looking for is a mapping, right? It's a mapping from X to a string, so to a binary string. right? And that binary string should tell me what the outcome of X is. Now, I could represent this using 2 bits, right? So I map 0 to 0, 0, 1 to 0, 1, and 2 to 1, 0, right? So if you see 0, 0, 0, then you know that the outcome was 0. If I observe 0, 1, then I know that the outcome was 1. If I observe 2, if it's 1, 0, then I know that the outcome was 2. Now this is assuming that I use the same number of bits to represent each of these values. Now what I can instead do is the following. Maybe for 0, I represent this using just the bit 0. 1 could be represented using maybe 1, and 2 could be represented using 1, 0, right? So if I observe, so if I want to convey that the outcome was 0, then I represent it using a 1 bit, using just 1 bit. If the outcome is 1, then I represent it again using 1 bit, which is a 1. If the outcome is 2, then I represent it using 2 bits, which is 1, 0. Right. So in this particular case, what is the expected number of bits which is needed to convey the value of X? It is the probability of observing a 0 times 1, because I'm representing 0 using 1 bit, plus the probability of observing a 1 times 1 bit, plus probability of observing 2 times 2 bits, because 2 is represented using 1, 0, right? So suppose that so 0, 1, and 2 take probabilities, say half, 1/4, and 1/4, right? So what is the expected number of bits required to represent this? So, sorry, can you repeat that?
1.2.
1.25. Okay. So in some sense, this is the information content. This measures the amount of information contained in X, right?
So isn't it
Yes.
losing some information here? Like,
Why are you losing information here?
for example, the sequence came like 101.
Okay.
Then you can tell which sequence is in original, like in our X domain.
Can you repeat?
Like we need to decompress from that sequence, right? Like sequence of encrypted ones. So like if, for example, they take it as 101, then
So,
it can be 20, or it can be 101. Like, are you getting my point?
okay. So I do agree. I do get your point. So here I'm assuming that I'm trying to compress just a single symbol, not a sequence of symbols. And your point is well taken, and that is indeed something that you need to consider, because so here when I'm saying that I'm going to represent 0 using just 0 and 1 using just 1, the question was, now if the suppose that you're compressing a sequence of symbols, and the compressed symbols or the mapped symbols was 101, then this could have been the outcome of yeah, so this could be 1 followed by 0 followed by 1, or it could be 1, 0 followed by 1, correct? But again, at least in this particular example, I'm assuming that I'm studying just a single symbol and not a sequence of symbols.
Okay, sir.
Okay. Any other questions?
Sir.
Yes, please.
According to this, if the number of alphabets increases, the compression algorithm will work very less, right? The efficiency of compression algorithm will be less.
So certainly, if the size of the alphabet is larger, then the number of bits of information it contains is of course more.
So, okay.
Right. So, but we're talking about everything in a relative sense. So, in its uncompressed form, it takes a certain number of bits, but then after compression, maybe it could take less number of bits, and that depends on the statistics of the source, the probability distribution of X. Right.
Hello, sir.
Yes.
This is Adil. So in this model, I wanted to ask if there is any assumption on if the input like alphabet is finite or not.
So here we're assuming that the input alphabet is finite, because again, how if it is infinite, then probably this statement doesn't make too much sense,
Yeah,
because you will need an infinite number of bits to convey a single value of X. So that's a good point. Yes.
Yeah, depending on model also it may converge, right?
It may converge, but this statement in itself,
In
so this,
general.
the right hand side would be infinite.
Yeah.
So we'll see later on that although a source in itself could be continuous or discrete, at least for now, when we're talking about notions of information and so on, we will assume that the alphabet is finite.
Okay.
And so it could be infinite in the sense that it could be discrete but infinite, and we can still handle it. But if it is a continuous random variables, then everything breaks down. And we'll revisit continuous random variables maybe a few weeks into the course, and see how things are similar, but they're also very different.
Okay.
Any other questions? Right. So all of this is again sort of building intuition and understanding. So from the next class onwards, we'll make some formal definitions. We'll see formal definitions of quantities, and we'll define what is called the entropy of a random variable, which in some sense characterizes the information content. The entropy is not exactly this information that I've defined, but we'll see that it is something that is close, and we'll see how that comes up in the context of compression. We'll see that entropy as a quantity arises naturally as a solution to the problem of compression, and going on, we'll see more such definitions. So basically, what we'll be interested in are objects of the following form. So we have a random variable, and we want to know how much information is contained in this random variable. Or given two random variables, we want to know. Yes.
Sorry, sir, to disturb you. Like some of us have classes now.
Oh yes, please go ahead. Yeah. So I'm wrapping up now. But yeah. So all that I want to say is that, so if we have two random variables, we want to know the amount of information that the second random variable contains about the first, and so on. So yeah, I agree. I'm over time. So let's wrap up for today. We'll meet again next week on Monday.